also that we have a S, which is just a non-empty subset of V. So it's non-empty. Well, let's now look at the following subset of V, of the vector space V. It's denoted in this way. So S, and then there's this symbol, perpendicular sign. Perpendicular, okay, S with this index, perpendicular index. Well, let's just define this new subset to be the following. So it just consists of all vectors from our vector space, which are orthogonal to all vectors from the given space S. So they're all orthogonal for all U from S. So this subset is called the orthogonal complement of S. Now, well, there are several important facts about this subset. So first of all, this set, the set S perpendicular is a vector subspace, is a linear subspace of V. And that's a very nice exercise. So please check it. That's not difficult. You just need to use a subspace test. However, what I would like to mention is the following fact. Which sort of tells us that whenever you have a subset and then you take its this subset of vectors orthogonal to a given subset, then these two subsets, the subspaces, indeed, they kind of behave nicely with respect to each other. Namely, they do not intersect, or say, to be precise, the intersection is just zero. And moreover, their sum gives us the whole vector space. So in other words, we can always get this kind of direct sum presentation of a vector space, right? Okay, so let me state it more formally. So suppose that we have a W, let W be a finite dimensional subspace of an inner product space. Space V, and let the vector V will be some vector, say from V. Then what we claim is that then there exists a unique vector say U from W and vector small w from the W perpendicular. So maybe yeah, I would like maybe, so there's another notation for this. Okay, let me, so this is a subspace, right? This is a subspace. Sometimes it's called orthogonal complement. So instead of saying each time we take S with this perpendicular symbol, I will say that we take the orthogonal complement, okay? So then, so for each U, so there exists a unique vector U and unique vector W from the orthogonal complement such that, well, V is just the sum. Well, indeed, since those two vectors are unique, so this is a unique sum, right? So in other words, the whole space V can be written as a direct sum of the space W and its orthogonal complement. Actually, if you look back at the definition of the direct sum, you will see that that's precisely what is stated here, right? So each vector is a sum of components, right? And then it's a unique choice. It's a unique choice, right? Which guarantees that the intersection of these two subspaces is 0. Okay, so moreover, well, let me mention moreover. If, say, V1 to Vn is an orthogonal basis, actually, it's better to take orthonormal basis because, as we know, it's kind of, we'll always have it, right? So orthonormal basis, or say basis of W, then, well, this vector U here, this one, can be computed using the formula which was given before. So it's sum from 1 to n of V comma Vi times Vi. Okay. Indeed, if you think a little bit about this, what is this formula? Well, this is what? This is a so-called projection formula, right? Look, I mean, we have a vector space, we have a subspace, and well, this formula just tells us that this vector U that we are going to find is just a projection. It's just a projection of V onto that subspace. Okay, let me just give a proof of this. So, well, basically, we just need to check that, well, okay, so first of all, let W be just the difference. So take our V, and subtract from this U given by this formula. Say, so it's V minus this sum. Okay, and then, well, clearly, well, of course, so what is U? U clearly belongs to W, right? Because why? Well, because look, I mean, this is a linear combination of those vectors Vi's, right? Maybe I should mention this. Yes, already mentioned. Okay, so okay, so let me mention. So that's U is in there since U is a linear combination of vectors from W, right? And on the other side, of course, it's clear just by the very definition that V is just U plus W. That's okay, right? Because we just took W to be the difference. So the last thing to check would be, we want to show now that this difference, this W, belongs to this orthogonal complement. Why that's so? Well, just enough to check that this W, I mean, if you take its inner product with each basis vector of W, then you get 0. So this W has to be orthogonal to all vectors from that capital W, right? So let me just, well, in this way, we just compute the inner product and got that, well, after substituting, we just substitute instead of W this formula, okay? So V minus the sum from I from 1 to n, V comma Vi, and then Vj. And then again, we use the same trick. We just expand this form. We just expand it, right? because this is linear with respect to the first coordinate. So we can expand it. And so we get this v comma vj minus the sum from I from 1 to n of v comma vi. And then we get vi comma vj. And then we observe that, look, I mean, this was chosen to be an orthonormal basis. So they're all orthogonal to each other. So meaning that in this sum, there's only one sum it will survive, namely the one corresponding to I equals j, right? So, well, so in this case, yeah, so let me maybe mention this. Right, okay, so let me, yeah, okay, so, right, so let me just put it like this, v comma vj minus, what will happen here? Well, look, I mean, here we'll just get v comma vj, well, I equals j, right? And then here we could just get vj comma vj, right? Because I equals j, right? And then, but then look, I mean, we were starting with an orthonormal basis. So all lengths are ones, right? So in particular, this guy is just one. So meaning that this difference, well, gives us just zero. So, and that's exactly what we wanted to show. So W is orthogonal to each basis vector of capital W. So this is from the orthogonal complement. Okay, well, finally, uniqueness. Why it's unique? Well, to show that it's unique, what do we do? Well, we proceed as usual, namely, well, suppose that there are two presentations. Say, suppose that V is U plus W on one hand side, and, well, let's also say U prime plus W prime from another side. Okay, where, well, say U prime is in W and W prime is in W, well, the orthogonal complement of W. Well, but then what can we do? I'll just subtract the left side from the right side. What do we get? Well, we get that, U minus U prime, right? This has to be the same as W. So U, it goes here. W goes there, W minus W, right? That's kind of clear, right? Just reshuffle the summons. But then look, I mean, both of them, this guy belongs to W and this guy belongs to the orthogonal complement. But then we know that this intersection, so they both belong to W and W perpendicular, so they belong to the intersection. But since the intersection is zero, so this has to be zero. Is the same as W prime minus W, it's the same as zero. So U is U prime and W prime is W. So they are unique, right? There are no other choices, no other choices. Okay. Right, as I already said, so some notation, right? So this vector is called the orthogonal projection. Okay. And so this vector is called the orthogonal projection. So what else? Yeah, so those coefficients, well, as I mentioned, those are Fourier coefficients, right? So maybe, yeah, that's it concerning the notation. Well, let me just mention the following consequence of this projection formula. That in this notation, so, well, let me mention that vector u, this orthogonal projection, is the unique vector in W that is closest to V in the following sense. So in the following sense, that if we just take any x from W and compute the difference between V and X, remember that this difference, this length of the difference, it actually computes the difference between two vectors, right? So then this will be always greater or equal than, oops. Then this will be always greater or equal than V minus U. So this inequality basically tells us that this vector U is the closest to V, right? Okay. Okay, so let me maybe check it. Yeah, well, still it's not clear why. However, it's kind of sort of it's clear from the sort of geometric point of view, right? I mean, if you remember the orthogonal projection, what is this, right? That's exactly kind of producing the closest vector, right? On the plane, on the linear subspace. However, let me now explain why this is the case for general inner product space. For general inner product space. So by the theorem, that I have mentioned, we have this presentation, right? V is, well, it's U plus W, where U is from W and small w is from the orthogonal complement. Now, well, choose our x, choose some x, okay? So say from W. Then what? Then, well, if you look at this difference, U minus X, then this one will be orthogonal to W, right? Why? Well, because we can just compute the inner product and see and check that this gives us 0. So U minus X comma W, what's that? This is just U comma W minus X comma W, right? And this is clearly 0. Because again, why this is the case? Because look, I mean, W belongs to the orthogonal complement. So this is orthogonal to any vector in capital W, right? So all these products are zeros. Both these products have to be zeros. Well, on the other side, we have the following. Well, let's just compare. Let's just look at V minus 6, the length of it. And let's look at its square. What's this? Well, this is just the same as U minus X, right? Plus W. Yes, so here what we just did, well, we just substituted this expression. And then, well, we can expand it. So there's a square here. Then we can expand it, right? And after careful expansion, so let me put brackets like this, plus w, comma, u minus 6 plus w. If I expand this using the standard properties of the inner product, what do I get? Well, actually, I will get, it's a nice exercise, I'll get the following: u minus 6 square plus w square. Yeah. And then, of course, this will be greater or equal than w square, because the sum of squares on the left, we just remove one non-negative square, right? And, well, this is actually, what is this? This is v minus u square. And that, well, now we can just take square roots from both sides, and we will get our inequality here. Again, this shows that this orthogonal projection indeed has some meaning, right? So basically, when you project, you just find the closest vector, right, on that subspace. Okay. So maybe I would like to now to state the following fact. So yeah, not maybe, I'm just going to state it. And after that, there will be a lottery. So those people who survive till the end of this lecture will be rewarded. Okay. Okay, good. So now here's a lemma. So suppose that S is V1 to Vk. Suppose that we are given an orthonormal set. Say maybe K here. So we say that is an orthonormal set in n-dimensional inner product space V. Okay, then the following hold. Then the following properties hold. First, AC. S can be extended to an orthonormal basis V1 to Vn of, here's n of V. So in other words, we can find extra vectors so that the whole list will form an orthonormal basis. Yeah? So second, so if W is the span of S, well then the complement, the thing that we add S prime Vk plus 1 to Vn is an orthonormal basis for the orthogonal complement of W. Basis for W, for the orthogonal complement. Okay, and C, well, if W is any subspace of V, well, then the dimension of V can be computed, well, it's just the sum of dimensions of W and of its orthogonal complement. It's a dimension of W and a dimension of its orthogonal complement. Okay, so right, so I leave the, I mean, I leave all these properties as an exercise, or you can actually look at the explanation on the lecture notes. So please don't forget to read lecture notes.